1977, we launched a machine into the void with no real idea what it would find. Now, nearly 50 years later, it's sending back data from a place no human-made object was ever designed to reach. And what it discovered there contradicts almost everything we thought we knew about where our solar system ends and the rest of the universe begins. Voyager 2 never visited Pluto. That detail matters because the journey it actually took was far stranger. While its twin, Voyager 1, got redirected to study Saturn's moon Titan, Voyager 2 kept going, past Jupiter, past Saturn, all the way to Uranus and Neptune, ice giants no spacecraft had ever seen up close. Then it just kept moving outward into territory we'd only theorized about. On November 5th, 2018, something shifted in the data streaming back from 11 billion miles away. The instruments detected a sudden drop in solar particles. Cosmic rays from deep space spiked dramatically. The solar wind, that constant stream of charged particles flowing from our sun, simply vanished. Voyager 2 had crossed an invisible boundary most people don't even know exists. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. This wasn't just empty space beyond Pluto. This was interstellar space, the region between stars where our sun's influence finally surrenders to the galaxy itself. What makes this crossing revolutionary isn't just that we reached it. It's what the spacecraft found when it got there, a boundary that shouldn't behave the way it does. Plasma compressed by forces we can't fully explain. Magnetic fields aligned in directions that violate our predictions. And a protective bubble around our solar system that appears far more complex than the simple sphere we'd imagined. The data contradicts itself in fascinating ways. Voyager 2 measured plasma 20 times denser than what fills our solar neighborhood. But the temperature readings came back almost double what every model predicted, between 30 and 50,000 Kelvin instead of the expected 15 to 30,000. That's not a minor discrepancy you can chalk up to instrument error. Here's what should have happened. As the spacecraft crossed from the heliosphere into interstellar space, the magnetic field should have rotated. Solar magnetic influence should have given way to galactic magnetic forces, creating a measurable shift in orientation. Every theoretical model predicted this rotation. Voyager 1 had already failed to detect it 6 years earlier, but scientists figured that might be a fluke, maybe something unique about where Voyager 1 crossed. Then Voyager 2 crossed at a completely different location and found exactly the same thing. No rotation. The magnetic fields inside and outside the heliosphere were parallel, aligned in ways that make no sense according to our understanding of how these forces should interact. 2 data points from 2 different parts of the boundary, both showing the same impossible result. The implications ripple outward from there. If the magnetic field doesn't behave as predicted at the heliopause, then our models of how the sun interacts with interstellar space need fundamental revision, which means our understanding of how other stars create protective bubbles around their planetary systems might be wrong too. But the magnetic mystery is just one layer. The boundary itself turned out to be far more permeable than expected. Scientists discovered the heliosphere leaking, particles from inside our solar bubble trickling out into interstellar space. And it's not symmetric. Voyager 1, which crossed near the front of the heliosphere, relative to our solar system's motion through the galaxy, found interstellar material leaking inward. Voyager 2, crossing more toward the flank, found solar material leaking outward. This two-way exchange suggests something dynamic happening at the boundary, not a static wall, but an active interface where solar and galactic forces engage in some kind of complex interaction we're only beginning to map. The heliosphere isn't a simple bubble. It's more like a living membrane with varying permeability in different regions. The crossing itself happened far faster than anyone expected. Voyager 1 took 28 days to fully transition from the heliosphere into interstellar space. Voyager 2 did it in less than 1 day. Same boundary, radically different experience. The spacecraft encountered what scientists call a clean break, rather than the gradual transition zones Voyager 1 had navigated. What creates these differences? Location appears to matter enormously. Voyager 1 crossed through a stagnation region where plasma flow nearly stopped, creating a kind of buffer zone before the final boundary. This region extended across 8 astronomical units, roughly the distance from Earth to Saturn. Voyager 2 encountered no such region. It passed through a transition area where solar plasma began changing direction and strength, then hit the boundary layer where cosmic rays increased, then punched straight through into interstellar space. The fact that these two spacecraft, crossing just a few years apart at roughly the same distance from the Sun, experience such different boundary conditions tells us the heliopause isn't uniform. It has structure, variation, complexity we hadn't anticipated. The nose of the heliosphere, pushing forward through the interstellar medium like the bow of a ship, encounters different pressures than the flanks. This creates asymmetries in the boundary that fundamentally alter how particles and fields behave in different regions. Distance presents its own challenge to understanding what's happening out there. Right now, Voyager 2 sits more than 13 billion miles from Earth. Light takes 16.5 hours to make that journey. Every command sent to the spacecraft requires that much time to arrive, and any response takes another 16.5 hours to return. A round-trip conversation takes 33 hours. NASA maintains contact through a single antenna in Australia, the only dish in the southern hemisphere capable of reaching Voyager 2's trajectory below the ecliptic plane. The spacecraft transmits data at 23 watts, about the power of a refrigerator light bulb, across a distance so vast it defies intuitive comprehension. And yet, we still receive coherent scientific measurements from instruments that were built in the 1970s. Those instruments are failing, one by one. The spacecraft runs on plutonium-238, which decays at a predictable rate, losing about 4 watts of power every year. In April 2023, engineers started tapping into backup power reserves meant for safety systems, buying a few more years of operation. Last October, they shut down the Plasma Science instrument to conserve energy for the remaining 4 sensors. Each instrument that goes dark represents data we'll never collect. The Plasma instrument, now silent, was the only one of its kind functioning when Voyager 2 crossed the heliopause. Voyager 1's equivalent sensor had failed decades earlier. That made Voyager 2's crossing invaluable because it could directly measure the plasma environment, providing the first empirical confirmation of the theoretical density jump that should occur at the boundary. The measurement came through on January 30th, 2019. plasma density of 0.039 particles per cubic centimeter, up from 0.002 inside the heliosphere. A factor of 20 increase, exactly matching predictions. Finally, one measurement that aligned with what the models said should happen. But even that confirmation came with complications. The density continued climbing as Voyager 2 traveled deeper into interstellar space. By October 2020, both Voyager spacecraft were detecting unexpected density increases in the very local interstellar medium. The space between stars, it turns out, has structure. Our solar system appears to be moving through a denser region of the local interstellar cloud. Or perhaps there are compression effects from interactions between different components of the interstellar medium that we don't yet understand. Think about what that means. The environment between stars isn't uniform empty space. It has currents, densities, temperature variations, magnetic structures. The galaxy is filled with invisible architecture that shapes how star systems move and evolve. We're mapping that architecture for the first time with two spacecraft that were never designed for this mission. The original Voyager program had a simple goal: visit Jupiter and Saturn during a rare planetary alignment that happens once every 176 years. 4-year mission. Both spacecraft completed those objectives by 1981. Everything since then has been bonus science from instruments running 40 years past their expiration date. Neptune was Voyager 2's last planetary encounter in 1989. The spacecraft discovered 6 new moons, observed the Great Dark Spot Storm System, and found that Neptune radiates more heat than it receives from the Sun. Its flyby of Triton revealed active nitrogen geysers erupting from a moon that should be geologically dead. Then Voyager 2 kept going into the darkness beyond. For 29 years, it traveled through the outer reaches of the heliosphere, that vast region of space dominated by the solar wind. Scientists knew the heliopause existed somewhere out there. They'd calculated rough distances based on theoretical models, but nobody knew exactly what crossing it would look like or what we'd find on the other side. The first hints came in August 2018, when the Cosmic Ray Instrument detected increasing numbers of galactic particles. These are high-energy particles accelerated by supernova explosions across the galaxy, traveling through interstellar space at nearly the speed of light. The heliosphere blocks most of them, protecting the inner planets from radiation that would make life far more difficult to sustain. As Voyager 2 approached the boundary, more cosmic rays started getting through. Then, on November 5th, the solar particles dropped sharply while cosmic rays spiked. The solar wind speed decreased to almost nothing. Multiple instruments simultaneously registered the transition, leaving no doubt about what had happened. The spacecraft had entered a realm where material from dying stars dominates. Plasma enriched with heavy elements from supernovas that exploded millions of years ago. This is the recycled matter that forms new stars and planets, the raw material of galactic evolution. By directly sampling it, Voyager 2 provides data about the composition of the interstellar medium that no telescope can match. But here's what keeps scientists puzzled. Voyager 2 isn't in pristine interstellar space. Both Voyager spacecraft appear to be in a perturbed transitional region just beyond the heliosphere, a boundary layer where solar and interstellar influences still mix rather than a clean separation between two distinct environments. The Sun's impact extends beyond its formal boundary. Coronal mass ejections, Those massive eruptions of plasma from the Sun's surface create shock waves that propagate past the heliopause into interstellar space. Voyager 2's instruments detect these waves, temporarily suppressing cosmic ray levels, even though the spacecraft has left the heliosphere. The Sun's influence reaches farther than the region it directly controls. This raises questions about where the solar system truly ends. Is it the heliopause where the solar wind stops? Is it the Oort cloud, that distant shell of comets extending perhaps a light year from the Sun? Is it wherever the Sun's gravity finally surrenders to the galactic tide? We don't have clear answers because we've only just begun exploring these outer boundaries. What we do know is that the boundary we've crossed isn't what we expected. It's more complex, more variable, more dynamic than the simple spherical shell our models predicted. The heliosphere responds to the 11-year solar cycle, expanding and contracting as solar activity waxes and wanes, except it doesn't contract as much as it should. Both Voyager spacecraft crossed at nearly identical distances, despite the solar cycle being in different phases. In 2012, when Voyager 1 crossed, solar activity was relatively high. In 2018, when Voyager 2 crossed, solar activity was lower. The heliosphere should have been smaller in 2018, but the crossing distances were almost the same. The interstellar magnetic field, measured at 7 microgauss by Voyager 2, appears to stabilize the boundary like a straitjacket, preventing the expansion and contraction that solar variations should cause. That magnetic field strength was itself a surprise. Predictions put it around 3 to 4 microgauss. Finding it nearly double that value means the interstellar medium exerts more pressure on the heliosphere than we'd calculated. This stronger external pressure helps explain the boundary's stability, but creates new questions about the local galactic environment. The data keeps arriving, transmitted across billions of miles, at a rate that would make dial-up internet seem blazing fast. 23 watts of power, carrying information about magnetic fields, plasma densities, cosmic ray counts, and particle compositions from a place we'll never visit in person. At least not in any time frame that matters to current human civilization. But those measurements are reshaping how we understand our place in the galaxy. The heliosphere isn't just our solar system's boundary. It's a laboratory for studying how stars interact with the interstellar medium. Every star with planets likely creates a similar protective bubble. Understanding ours helps us understand theirs, and that has implications for habitability. Galactic cosmic rays are dangerous. They damage DNA, destroy complex molecules, and make planetary surfaces hostile to life as we know it. A star's protective bubble shields its planets from this radiation. The strength and structure of that bubble might determine whether life can emerge on worlds orbiting distant suns. Voyager 2's measurements provide the first direct data about how these protective systems function. The spacecraft continues traveling outward at 34,320 miles per hour relative to the Sun. Every day, it moves another 800,000 miles deeper into interstellar space. The instruments that remain active keep collecting data, sending back measurements of an environment humanity has never sampled before. How long can it continue? Engineers estimate they can maintain some instruments until the early 2030s maybe. After that, power levels will drop below the threshold needed to operate the transmitter. Voyager 2 will fall silent, becoming a derelict monument to human curiosity, carrying a golden record with sounds and images from Earth towards stars it will reach in 40,000 years. But before that silence comes, before the last instrument shuts down and the final transmission ends, Voyager 2 has one more mystery to help us unravel. Because what it found beyond the heliopause wasn't just empty space or simple plasma. It discovered a boundary with memory, a region where past and present collide in ways that challenge our fundamental understanding of how cosmic boundaries work. Memory lives in plasma, apparently. Not biological memory, magnetic memory encoded in particle densities and field alignments. When Voyager 2's magnetometer detected that peculiar alignment between solar and interstellar magnetic fields, it revealed something physicists hadn't predicted. The boundary remembers where it's been. Both spacecraft measured magnetic fields running parallel on either side of the heliopause. Scientists expected rotation. The solar magnetic field should have twisted as it met the galactic field, creating a clear directional change. Instead, the fields lined up like dancers matching their partners' movements. That alignment shouldn't persist. Magnetic fields in plasma are fluid, constantly shifting as charged particles flow through them. Yet somehow, the heliopause maintains this parallel structure. The explanation might lie in magnetic reconnection events that happened years or decades before the spacecraft arrived. When magnetic field lines from different sources meet, they can snap and reconnect in new configurations. Those reconnection events would release energy and create lasting structural changes. The boundary we measure today bears the scars of past interactions, frozen into its magnetic architecture. This isn't the only evidence of temporal effects at the heliopause. Voyager 2 detected something stranger: particles from the Sun leaking outward into interstellar space. Not just a few stray protons, but a measurable trickle of solar material crossing the boundary. The spacecraft's position near the heliosphere's flank revealed a more porous boundary than Voyager 1 found at the nose. Different locations, different permeability. But Voyager 1 had discovered the opposite phenomenon: interstellar material streaming inward across the boundary. The heliopause apparently allows bidirectional leakage, though scientists can't explain the mechanism. Magnetic reconnection could create temporary tunnels through the boundary, or perhaps wave activity in the plasma generates transient holes. Either way, the boundary isn't the clean separation we imagined. It's more like a semi-permeable membrane with selective permeability that varies by location and time. That temporal variation showed up in another measurement. Before Voyager 1 crossed the heliopause, its instruments detected two pocket regions where galactic magnetic field had penetrated deep into the heliosphere. These incursions brought cosmic radiation with them, creating temporary zones where the Sun's protective influence had been compromised. The pockets eventually closed, but their existence proved the boundary's dynamic nature. Voyager 2 encountered no such pockets during its crossing. 6 years separated the two crossings. The boundary had changed its behavior between visits, reorganizing itself in response to solar activity variations or random fluctuations in the interstellar medium. What one spacecraft measured doesn't necessarily predict what the other will find. The crossing itself highlighted these differences. Voyager 1 spent 28 days in a stagnation region where plasma motion dropped nearly to zero, an 8.6 astronomical unit wide zone where the solar wind had slowed to a crawl, creating a strange liminal space, neither fully heliospheric nor fully interstellar. Voyager 2 blasted through the boundary in less than a day, experiencing no stagnation zone at all, just a clean transition from solar wind to interstellar plasma within hours. Temperature measurements added another layer of complexity. The plasma science instrument on Voyager 2, the one Voyager 1 lacked, measured temperatures between 30,000 and 50,000 Kelvin in the near interstellar environment. Models had predicted 15 to 30,000. Finding temperatures nearly double the expectation suggests compression heating. When interstellar plasma encounters the heliosphere, it compresses like air squeezed in a piston. Compression raises temperature, but the degree of heating exceeded predictions, implying stronger compression than models accounted for. That compression appears on both sides of the boundary. Voyager 2 measured increasing plasma density just before crossing the heliopause, indicating compressed plasma on the heliosphere's interior edge. Then it measured the elevated temperature on the exterior side, showing compression there too. The boundary itself acts as a compression zone, squeezing plasma from both directions. What creates that bidirectional compression? The interstellar magnetic field exerts pressure from outside. The solar wind pushes from inside. Where they meet, plasma gets caught between opposing forces and compresses. But the mathematics of that compression don't quite balance with observations. Something else is contributing pressure that models haven't captured. October 2020 brought a new puzzle. Astronomers analyzing Voyager data noticed increasing density in the very local interstellar medium. Not just the jump at the heliopause, that 20-fold increase was expected, but a gradual density rise as both spacecraft traveled deeper into interstellar space. The density gradient suggested large-scale structure in the interstellar cloud surrounding our solar system. Our solar system moves through the galaxy at roughly 43,000 miles per hour, plowing through interstellar material like a boat through water. That motion should create a bow shock ahead of the heliosphere, similar to how a boat's bow creates waves. The increasing density Voyager measured might indicate we're approaching a denser region of the local cloud. Or it could mean the cloud itself has internal structure, layers of varying density stacked like atmospheric strata. Either interpretation has implications. If we're moving into denser material, the heliosphere might shrink over the next few thousand years. Increased external pressure would compress the boundary inward, potentially exposing the outer planets to higher cosmic radiation levels. If the cloud has layered structure, that tells us something about how interstellar material organizes itself in the galaxy. The plasma waves Voyager 2 detected revealed more about this environment. Plasma doesn't sit still. It oscillates, creating waves that propagate through the medium like sound waves through air. The spacecraft's plasma wave instrument detected electron plasma oscillations with specific frequencies determined by electron density. By measuring those frequencies, scientists could calculate density with remarkable precision. The first measurement came on January 30th, 2019, nearly 3 months after crossing the heliopause. Density: 0.039 electrons per cubic centimeter with 15% uncertainty. That matched almost exactly with Voyager 1's first measurement from 6 years earlier. Both spacecraft found similar densities at similar distances, confirming the heliopause location and structure despite the 6-year gap. But those measurements also revealed something unexpected about cosmic ray propagation. When the Sun ejects a coronal mass ejection, a massive burst of plasma and magnetic field. It creates a shock wave that ripples outward through the heliosphere. Scientists knew those shocks could reach the heliopause. What they didn't know was whether they could cross into interstellar space. Voyager 2's data answered that question. Coronal mass ejections do cross the boundary, creating shock waves that propagate into the local interstellar medium. Those shocks temporarily reduce cosmic ray levels as they pass, creating measurable dips in the cosmic radiation environment. The Sun's influence doesn't stop at the heliopause. It extends into nearby interstellar space through these shock waves. That finding has implications for understanding stellar winds beyond our solar system. Every star with magnetic activity likely produces similar shock waves that propagate into its local interstellar environment. Those shocks could affect planetary atmospheres dozens of astronomical units away from their host stars. They might trigger chemical reactions in interstellar clouds. They could even influence star formation in nearby regions. The cosmic ray measurements themselves show dramatic changes at the crossing. Solar energetic particles, charged particles accelerated by the Sun's magnetic field, dropped to nearly zero within hours. Galactic cosmic rays, particles accelerated by supernovae and other energetic events across the galaxy, increased by roughly 20% and stayed elevated. The transition was sharp and definitive. Before the crossing, the heliosphere blocked more than 70% of galactic cosmic radiation from reaching the inner solar system. After crossing, Voyager 2 measured the full intensity of galactic radiation for the first time. That radiation level represents what every planet in the solar system would experience without the heliosphere's protection. It's enough radiation to sterilize planetary surfaces, break apart complex organic molecules, and damage DNA in any unprotected organism. Earth's magnetic field and atmosphere provide additional shielding, but the heliosphere is our first line of defense. Planets without that protection face a much harsher radiation environment. Which brings us back to the question of habitability around other stars. Understanding our heliosphere's structure and behavior provides a template for evaluating how other stellar protective bubbles function. A star's mass, magnetic field strength, and stellar wind properties determine its heliosphere's size and effectiveness. Those factors could be as important as the planet's location in the habitable zone for determining whether life can emerge and survive. Voyager 2's measurements let us test theories about stellar wind interactions with the interstellar medium. The data constrains models of how stars of different types create protective environments around their planets. When we evaluate exoplanets for habitability, we can now factor in estimates of their host stars' heliospheric protection based on what we've learned from our own. But the data keeps surprising us. The magnetic barrier Voyager 2 encountered before crossing the heliopause spanned 0.7 astronomical units, roughly the distance from the Sun to Venus. In this transition zone, the solar magnetic field strength tripled as it compressed against the interstellar field. After crossing, the field strengthened further as the galactic magnetic field dominated. Voyager 1 didn't detect such a clear magnetic barrier structure. Different crossing locations produce different magnetic signatures. The heliosphere isn't uniform around its perimeter. It has regional variations that depend on the spacecraft's position relative to the direction of solar system motion through the galaxy. That non-uniformity extends to the crossing speed. less than 1 day for Voyager 2 versus 28 days for Voyager 1. The difference suggests the heliopause has thin and thick sections. Where Voyager 2 crossed, the boundary was relatively abrupt, a sharp transition from one regime to another. Where Voyager 1 crossed, the boundary was drawn out over a large distance with multiple transition zones. Why the difference? Position matters. Voyager 1 crossed near the heliosphere's nose, where it plows forward through the interstellar medium. That region experiences the strongest compression from the interstellar wind. Voyager 2 crossed near the flank, where pressure from the interstellar wind is lower. Lower pressure means a simpler boundary structure. The flank location also explains the greater permeability Voyager 2 measured. With less compression, the magnetic field lines don't pack as tightly. Gaps can form where particles slip through. The nose region, under higher pressure, maintains a tighter magnetic field structure that blocks particle exchange more effectively. These spatial variations matter for understanding the heliosphere's overall geometry. It's not a perfect sphere. It's elongated in the direction of motion, with a blunt nose and trailing tail. The boundary thickness, permeability, and magnetic structure all vary depending on position around this complex three-dimensional surface. Both spacecraft are still traveling through what scientists call the boundary layer, a perturbed region just beyond the heliopause where solar and interstellar influences continue mixing. This isn't pristine interstellar space. It's a transitional environment where the sun's effects gradually fade but haven't completely disappeared. How far does this boundary layer extend? We don't know. It could be a few astronomical units or dozens of astronomical units thick. Voyager 2 continues measuring plasma density, magnetic field strength, and cosmic ray levels as it travels deeper into interstellar space. Eventually, those measurements should stabilize, indicating the spacecraft has finally reached undisturbed interstellar conditions. But eventually might mean years or decades. The spacecraft moves at 34,000 miles per hour, fast by human standards, glacial by astronomical ones. Each astronomical unit takes roughly 2 months to traverse. If the boundary layer extends 10 astronomical units beyond the heliopause, Voyager 2 won't exit it until the mid-2020s. If it extends further, the spacecraft might run out of power before reaching truly pristine interstellar space. That power situation grows more critical each year. The radioisotope thermoelectric generators lose 4 watts annually. Engineers have already shut down the plasma science instrument to conserve power. Other instruments will follow. By the early 2030s, power levels will drop below the threshold needed to operate the transmitter. Then silence. But before that silence, Voyager 2 has revealed something profound about cosmic boundaries. They're not static barriers, but dynamic interfaces with memory, structure, and behavior that changes across time and space. The heliopause isn't just where the sun's influence ends. It's where past and present collide, creating a boundary that remembers its history while continuously adapting to new conditions. That persistent signature from the sun, coronal mass ejections, reaches far beyond where anyone expected. These massive eruptions of solar material punch through the heliopause and temporarily suppress cosmic ray levels on the interstellar side. The effect shows up clearly in Voyager 2's data. When a CME shockwave passes, cosmic ray counts drop for weeks or months before gradually recovering. This wasn't supposed to happen, Once you cross the heliopause, you're beyond the sun's domain. The protective bubble ends. Interstellar space begins. Clean separation, right? Not quite. The sun's influence bleeds through. Those shock waves propagate into the very local interstellar medium, creating ripples that Voyager 2 can measure from billions of miles away. It's like standing outside during a thunderstorm and still feeling the pressure waves from distant lightning strikes. You've left the storm's center, but its energy reaches you anyway. This extended influence matters for understanding stellar environments across the galaxy. Every star produces a wind. Every star generates a protective bubble. Every star's bubble interacts with the surrounding interstellar medium. What Voyager 2 measures here applies everywhere. The mechanics might differ: different wind strengths, different interstellar densities, different magnetic field configurations, but the fundamental physics remains constant. That universality makes these measurements invaluable for exoplanet studies. When astronomers discover planets orbiting distant stars, they need to assess habitability. Liquid water matters. Atmospheric composition matters. But so does radiation shielding. A planet in the habitable zone might still be sterilized by cosmic rays if its star's protective bubble is too weak, or if the local interstellar environment is too harsh. Voyager 2's data provides the baseline. This is what a Sun-like star's interaction with the interstellar medium looks like up close. These measurements help calibrate models used to estimate radiation environments around other stars. Without this ground truth, those models rest on theoretical foundations alone. The spacecraft continues measuring that radiation environment. Cosmic ray levels remain elevated, but show subtle variations. Some of those variations correlate with solar activity, CMEs punching through, temporarily creating low-density regions in the cosmic ray background. Others don't correlate with anything obvious. Random fluctuations in the interstellar medium itself, perhaps. Density inhomogeneities in the local cloud. Shock waves from distant stellar events reaching our neighborhood. That local cloud, the local interstellar cloud, capital L and I for the astronomers keeping track, is where our solar system resides. It's a relatively warm, low-density region of space created by ancient supernovae that cleared out the surrounding medium. The cloud stretches for tens of light years in various directions. We've been traveling through it for tens of thousands of years, and will continue for tens of thousands more. Voyager 2 is sampling this cloud directly. Every plasma measurement, every magnetic field reading, every cosmic ray count adds detail to our understanding of its structure. The density measurements show variations: 0.039 particles per cubic centimeter in one region, slightly higher or lower elsewhere. Those variations hint at internal structure within the cloud itself. Temperature measurements reveal similar complexity: 30,000 to 50,000 Kelvin. That's hot by everyday standards, but cold for ionized gas in space. The elevated temperature results from compression as the interstellar medium encounters the heliosphere. Like air heating up in a bicycle pump, the plasma compresses, temperature rises. But how much of that heat comes from compression versus other sources? That question remains open. Some of the heating might come from magnetic reconnection events at the heliopause. Some might come from turbulence in the interstellar medium itself. Disentangling these contributions requires more data. Voyager 2 provides that data one measurement at a time. The magnetic field strength continues to surprise researchers. 7 microgauss. That's stronger than theoretical models predicted before Voyager 1's crossing. Models expected 3 to 4 microgauss based on observations of polarized starlight passing through the local interstellar medium. Instead, both spacecraft measure fields nearly twice that strong. Why the discrepancy? One possibility: the local field is genuinely stronger than the average field in the surrounding region. We're measuring a specific location in space, not the average over large volumes. Just as Earth's magnetic field varies in strength depending on where you measure it, the interstellar magnetic field probably has local variations too. Another possibility: the measurements aren't capturing the same thing. Polarized starlight measurements average over long sight lines through space. They smooth out local variations. Voyager's magnetometer measures the field right at the spacecraft's location. No averaging, no smoothing. Just the local field strength at that specific point. Either way, that strong field acts as a straitjacket on the heliosphere. The interstellar magnetic field presses against the solar magnetic field at the heliopause. That pressure helps stabilize the boundary. Without it, the heliopause would flex and breathe more dramatically as solar wind pressure varies over the solar cycle. Instead, the boundary maintains relatively constant size despite those variations. That stability showed up in the crossing distances. Voyager 1 crossed at 121.6 astronomical units. Voyager 2 crossed at 119 astronomical units. Nearly identical despite crossing 6 years apart at different phases of the solar cycle. The solar wind was weaker during Voyager 2's crossing than during Voyager 1's. The heliopause should have been pushed inward, making Voyager 2 cross at a smaller distance. It wasn't. The interstellar magnetic pressure held firm. This tells us something fundamental about boundary physics. The heliopause isn't just a pressure balance between outward solar wind and inward interstellar plasma. It's a magnetic pressure balance too. The field strengths on both sides contribute as much as the particle pressures, maybe more. That magnetic contribution creates the parallel field alignment that puzzled researchers. Both spacecraft measured magnetic fields pointing in the same direction on both sides of the heliopause. No rotation, no twist, just smooth alignment. Theory predicted rotation. The solar magnetic field points one direction. The interstellar magnetic field points another. When you cross from one to the other, you should see the field direction change. Like crossing from the northern hemisphere to the southern hemisphere on Earth and watching compass needles flip from pointing north to pointing south. Except it didn't happen at either crossing. This suggests the fields are already aligned before the spacecraft crosses. But why? What mechanism enforces that alignment? One hypothesis involves magnetic reconnection. The solar and interstellar fields press against each other at the heliopause. When oppositely directed field lines meet, they can reconnect, breaking and rejoining in new configurations. That reconnection might align the fields, creating a layer where both point the same direction. But reconnection typically creates turbulence and heating. Voyager 2 didn't observe obvious reconnection signatures. No sudden temperature spikes, no turbulent magnetic field fluctuations, just smooth alignment. Another hypothesis suggests the local interstellar field happens to point in a direction similar to the solar field at these crossing locations. Pure coincidence. The fields align not because any physical mechanism forces them to, but because the spacecraft crossed at locations where they happened to point the same way. Testing that hypothesis requires more crossings. 2 spacecraft at 2 locations isn't enough to determine whether the alignment is local coincidence or global necessity. You need measurements from multiple positions around the heliosphere. Unfortunately, we don't have those measurements. Voyager 1 and 2 are the only spacecraft to cross the heliopause. Nothing else is close. New Horizons might reach the heliopause eventually. It's on an escape trajectory after its Pluto flyby, but it's moving slower than the Voyagers, about 31,000 miles per hour versus their 34,000. The crossing won't happen for decades. By then, New Horizons might not have enough power to operate its instruments. That power constraint haunts all interstellar missions. Voyager 2's radioisotope thermoelectric generators produce electricity from plutonium-238 decay. Predictable, reliable, but finite. 4 watts less each year. By April 2023, power levels dropped enough that engineers started tapping backup reserves intended for safety systems. That bought a few more years of operation, not many. October 2024 brought the first major instrument shutdown. The Plasma Science instrument, the one that made those crucial density measurements confirming the heliopause crossing, went offline. Permanently. Not because it failed, because there wasn't enough power to keep it running along with everything else. 4 instruments remain active. The magnetometer, 2 energetic particle detectors, the cosmic ray subsystem. Each one continues gathering data as Voyager 2 ventures deeper into interstellar space. But one by one, they'll fall silent too. Another shutdown in 2025. Maybe one in 2027. By the early 2030s, power levels will drop below the threshold needed to operate the transmitter. Then all contact ceases. Even after that final shutdown, Voyager 2 will continue traveling. Its trajectory carries it away from the Sun at 34,000 miles per hour, silent but moving. In 40,000 years, it'll pass within 1.7 light-years of Ross 248, a small red dwarf star in the constellation Andromeda. In 300,000 years, it'll reach the outskirts of the Oort cloud, that distant shell of comets marking the solar system's true edge. But we won't know what it finds there. No instruments will function. No transmitter will send data home. The spacecraft becomes an artifact, a message in a bottle drifting through the cosmic ocean. The golden record attached to its side carries sounds and images from Earth, greetings in 55 languages, music from different cultures, pictures of human life and achievement. If another civilization ever intercepts Voyager 2, that record provides context. This is who built us. This is where we came from. Until then, these final years of operation matter intensely. Every measurement adds to humanity's understanding of interstellar space. Every data point helps answer questions about the environment beyond our protective bubble. What's the density distribution in the very local interstellar medium? How does it vary as you move away from the heliopause? What's the temperature profile? How strong is the magnetic field at different locations? These questions matter for planning future interstellar missions. Concepts exist for dedicated interstellar probes, spacecraft designed from the start to explore the space between stars. Faster trajectories, more advanced instruments, power systems that last longer. Some designs propose nuclear electric propulsion. Others suggest solar sails accelerated by laser arrays. One concept involves riding the shockwave from a nuclear detonation. All of them need to know what they'll encounter. Voyager 2's measurements provide that knowledge. The density, temperature, magnetic field strength, cosmic ray levels. These aren't just abstract numbers. They're engineering constraints. They determine shielding requirements. They affect trajectory planning. They influence instrument design. But those future missions remain concepts. Nothing's funded. Nothing's built. Voyager 2 is out there now, gathering data we can't get any other way. When its power runs out, that data stream ends. We'll still have theoretical models. We'll still have remote observations. But we won't have direct measurements from a spacecraft physically present in interstellar space. That makes these remaining years precious. Engineers manage power consumption with obsessive care. Every instrument shutdown is agonizing. Each one represents capabilities lost forever. But shutting down instruments extends the mission. Every watt conserved is more time for the remaining instruments to gather data. The current trajectory suggests operations into the early 2030s, maybe 2032, possibly 2033 if everything breaks right. That gives Voyager 2 roughly another decade to explore. A decade to measure density variations in the local cloud. A decade to track magnetic field changes. A decade to monitor cosmic ray fluctuations. What will it find during that decade? Nobody knows. The boundary layer might extend far enough that Voyager 2 remains in perturbed space for years to come. Or the spacecraft might cross into truly pristine interstellar conditions next year. The measurements will reveal which. Those measurements also reveal something about scientific exploration itself. Voyager 2 launched in 1977 with a 4-year primary mission to Jupiter and Saturn. That mission succeeded spectacularly, but the spacecraft kept going. Extended mission to Uranus, then Neptune, then interstellar space. Each phase revealed phenomena nobody predicted. The heliopause's variable structure, the magnetic field alignment mystery, the leaky boundary allowing bidirectional particle exchange, the compressed plasma regions, the elevated temperatures, the stronger than expected magnetic field. None of these discoveries appeared in the mission's original objectives. They emerged because the spacecraft was there, measuring, recording, transmitting data back to Earth. That pattern repeats throughout science. Design for one goal, achieve it, then discover the real breakthroughs happen afterward. The Hubble Space Telescope was supposed to last 15 years. It operated for 34 before retirement. The Mars rovers Spirit and Opportunity were designed for 90 days. Spirit lasted 6 years. Opportunity, 15. Cassini's 4-year mission at Saturn extended to 13. Each extension revealed phenomena nobody anticipated. But Voyager 2 stands apart from these examples. Spirit and Opportunity remained on Mars. Cassini stayed at Saturn. Hubble orbited Earth. They extended missions within familiar environments. Voyager 2 crossed into territory no human-made object had ever entered before. It didn't just exceed expectations, it redefined them entirely. The spacecraft's trajectory through interstellar space reveals patterns nobody predicted. Density measurements show the local interstellar medium isn't uniform. It varies, sometimes significantly. October 2020 brought detection of an unexpected density increase. Not a small fluctuation. A substantial gradient suggesting our solar system is moving through a denser region of the local cloud. Or perhaps compression effects from interactions between different components of the interstellar medium create these variations. Either way, the readings contradict assumptions about a smooth, featureless environment between stars. These density changes matter for understanding our solar system's motion through the galaxy. We're not sitting still. Our Sun orbits the galactic center at roughly 220 kilometers per second. During that journey, we pass through different neighborhoods, some dense, some sparse, some with strong magnetic fields, some with weak ones. The local interstellar cloud we're currently traversing extends maybe 30 light-years across. We've been inside it for perhaps 100,000 years. We'll exit in another few thousand. What happens when we leave? Nobody knows. The boundary between the local cloud and whatever lies beyond might be sharp or gradual. It might involve temperature changes, density shifts, magnetic field transitions. Voyager 2 can't answer that question. It won't survive long enough to reach the edge, but it's providing baseline measurements of what exists inside the cloud. Future missions will build on that knowledge. The temperature readings challenge theoretical predictions too. Models suggested interstellar plasma temperatures between 15,000 and 30,000 Kelvin. Voyager 2 measured 30,000 to 50,000 Kelvin, nearly twice the upper predicted range. Why? Compression heating as interstellar plasma encounters the heliosphere provides one explanation. Like air heating up when compressed. But the magnitude exceeds what simple compression should produce. Something else must be contributing. Turbulence, perhaps. Magnetic field interactions. Shock waves from distant stellar events. The measurements raise more questions than they answer. That happens constantly in frontier exploration. You expect certain conditions based on theory. Reality delivers different conditions. Then you scramble to understand why the theory missed something. Sometimes the theory's fundamentally wrong. More often it's incomplete. Missing variables, oversimplified assumptions, unaccounted interactions. Voyager 2's temperature measurements don't invalidate heliosphere models. They refine them. Force theorists to consider additional heating mechanisms they'd previously dismissed as negligible. The magnetic field alignment mystery persists without resolution. Both Voyagers expected to detect field rotation at the heliopause. Solar magnetic field inside. Galactic magnetic field outside. They should orient differently. Simple logic. Except both spacecraft found alignment instead. The fields parallel each other. Scientists proposed magnetic reconnection to explain it. Temporary connections between solar and galactic field lines that realign them locally. Plausible, but reconnection should be sporadic. Variable. Instead, both spacecraft found consistent alignment despite crossing 6 years apart at different locations. That suggests something more fundamental than temporary reconnection events. One possibility involves the large-scale structure of galactic magnetic fields. Maybe the local galactic field happens to align with our solar magnetic field's orientation. Coincidence at cosmic scales. Another theory proposes that the heliosphere's motion through the interstellar medium creates a bow shock that reorients the galactic field ahead of it. Like water flowing around a moving ship's hull. The ship doesn't change the ocean's overall current, but it affects water's immediate direction near the hull. Our heliosphere might similarly affect the galactic magnetic field's local orientation without changing its larger structure. Testing these theories requires more data. One spacecraft measuring one location provides a data point. Two spacecraft measuring two locations provides a line. You need multiple measurements across different regions to map three-dimensional structure. Voyager 1 crossed the nose region, where the heliosphere plows forward. Voyager 2 crossed toward the flank. Both found alignment. Does that mean the entire heliopause shows alignment? Or did two spacecraft just happen to cross at aligned regions while other areas show rotation? No way to know without additional measurements. Future interstellar probes could provide them, if they get funded, if they get built, if they launch before everyone who worked on Voyager retires or dies. The leaky boundary discovery upends assumptions about the heliosphere's impermeability. Scientists envisioned a clean separation, solar particles inside, interstellar particles outside. Instead, both Voyagers found bidirectional exchange. Voyager 1 detected interstellar material streaming into the heliosphere. Voyager 2 found solar material escaping into interstellar space. Different directions, same phenomenon. The boundary isn't sealed, it's porous. Why? Magnetic reconnection offers one explanation again. Field lines from both sides connect and disconnect constantly. When they connect, they create temporary pathways for particles to cross. When they disconnect, those pathways close. The process repeats continuously, creates net particle exchange over time, even though no permanent gaps exist. Another possibility involves turbulence at the boundary, like waves on a beach. Sometimes water pushes inland, sometimes it retreats. The boundary position oscillates. During oscillations, particles from one side get caught on the other. Neither explanation fully satisfies researchers. Both might be partially correct, or something entirely different might be happening. Understanding boundary permeability matters for planetary protection. Earth sits deep inside the heliosphere. Cosmic rays from interstellar space must penetrate that boundary to reach us. The heliosphere blocks most of them. Voyager 1 measurements suggest it stops 70% of galactic cosmic radiation. But if the boundary's permeable, some radiation slips through areas where normal shielding breaks down. Does permeability vary with location? Does it change over time? During solar minimum, when the solar wind weakens, does permeability increase? These questions affect predictions about radiation exposure for future deep space missions beyond Earth's magnetosphere. The transitional boundary layer extends farther than anyone expected. Both Voyagers remain in perturbed space years after crossing the heliopause. Not pristine interstellar conditions, a mixed zone where solar and galactic influences still interact. How far does this layer extend? Unknown. Voyager 1 crossed in August 2012. 12 years later, it's still detecting signatures of solar influence. Coronal mass ejections from the Sun send shock waves through the interstellar medium. These shocks temporarily reduce cosmic ray levels, even billions of miles beyond the heliopause. The Sun's reach exceeds the formal boundary of its protective bubble. That has implications for defining where the solar system ends. The heliopause marks where the solar wind stops. Clear boundary, measurable transition. But solar influence continues beyond it. Gravitational influence extends much farther still. The Sun's gravity dominates out to perhaps 2 light-years, halfway to the nearest star. The Oort cloud of comets occupies that region. Solar gravity holds them in extremely distant orbits. Some comets take millions of years to complete one orbit. They're part of the solar system by gravitational definition, even though they're far beyond where the solar wind reaches. So where does the solar system actually end? Depends on your definition. Solar wind? Heliopause. Gravitational dominance, 2 light-years out. Orbital mechanics. Wherever the sun's gravity stops controlling objects' trajectories. No single answer satisfies all criteria. Voyager 2 crossed one boundary. Not the only boundary, just the one we can measure with current technology. The cosmic ray data reveals the heliosphere's protective function. Inside the boundary, cosmic ray levels stay relatively low. Outside, they jump dramatically. Factor of 3 increase in some energy ranges, factor of 5 in others. These aren't gentle particles. They're atomic nuclei accelerated to nearly light speed by supernova explosions. When they hit biological tissue, they cause damage. DNA breaks, cellular dysfunction, increased cancer risk. Earth's magnetosphere and atmosphere provide additional shielding. But spacecraft beyond that protection face the full cosmic ray environment. Understanding intensity variations matters for designing shielding for crewed missions to Mars or beyond. Voyager 2's measurements show cosmic ray levels fluctuate over time. They don't stay constant. Shock waves from solar eruptions push them down temporarily. Then they recover. Long-term trends show gradual increases as the spacecraft moves deeper into interstellar space. But the increases aren't smooth. They're jagged, variable, influenced by local conditions in the interstellar medium, by magnetic field configurations, by density variations, by turbulence. Predicting radiation exposure for a hypothetical crewed interstellar mission requires understanding these variations. Otherwise, you're designing shielding for average conditions that might not represent actual exposure during the journey. Communication latency highlights the mission's extreme distance. Commands take 16.5 hours to reach Voyager 2. Responses take another 16.5 hours to return. 33-hour round trip. If something goes wrong, you can't fix it quickly. You send a command, wait a day and a half, hope it worked. That delay shaped mission operations from the beginning. Everything gets planned carefully, multiple contingencies built in. Autonomous systems handle immediate problems. Ground controllers deal with long-term strategy. The spacecraft must survive on its own between communications sessions. That autonomy becomes more critical as power declines. Fewer instruments mean less redundancy. If the attitude control system fails, the spacecraft can't point its antenna at Earth. Communication ends. If the backup attitude control fails, no recovery option exists. The spacecraft continues forever through interstellar space, silent and dark, carrying its golden record as the only evidence it ever existed. Engineers work to prevent that outcome, but eventually power runs out regardless of how carefully they manage it. The October 2024 shutdown of the Plasma Science instrument marked a turning point. That instrument provided direct measurements of plasma density, temperature, and velocity. Critical data for understanding the interstellar environment. Turning it off wasn't a choice made lightly, but keeping it running meant losing another instrument sooner. The cosmic ray detectors, magnetometer, and low-energy charged particle instrument remain operational. They'll continue gathering data until power depletion forces additional shutdowns. Every instrument that goes dark represents capabilities lost permanently. No backup spacecraft exists to replace them. When Voyager 2's instruments fall silent, that data stream ends forever, unless something unexpected happens. Space missions sometimes surprise everyone. Voyager 2 itself provides the best example. Designed for 4 years, operating for nearly 50. Maybe the power lasts longer than predicted. Maybe engineers find additional reserves. Maybe new techniques for managing declining power extend operations beyond current projections. But probably not. Physics imposes hard limits. Radioactive decay proceeds at fixed rates. Power output decreases predictably. At some point, insufficient power remains to operate any instruments. That point approaches inevitably. When it arrives, Voyager 2 transitions from active explorer to passive artifact. It continues moving through interstellar space at 15.4 kilometers per second, heading toward no particular destination. In roughly 40,000 years, it'll pass within 1.7 light-years of Ross 248, a small red dwarf star. Not a close approach by planetary standards, just closer than it'll pass to anything else for a very long time. After that, it'll wander the galaxy for billions of years, maybe longer. The golden record might outlast everything humanity builds on Earth. Consider what survives. Pyramids erode, mountains wear down, continents drift, oceans evaporate, stars burn out. But in the vacuum between stars, nothing corrodes metal. No atmosphere, no weather, no geological processes. The record sits sealed inside its aluminum cover, protected from micrometeorites by the spacecraft's structure, traveling through an environment where decay operates on timescales that dwarf human comprehension. Whoever finds it encounters something peculiar. A flat disk, grooves spiraling inward, instructions etched on the cover showing how to extract information, diagrams explaining playback speed, the position of pulsars relative to our sun marking when and where this object came from, assuming they figure it out, assuming they possess technology capable of reading analog recordings, assuming their sensory apparatus processes information in ways compatible with audio and images. Big assumptions. The record contains 116 images, greetings in 55 languages, sounds from Earth, music spanning cultures and centuries. It's optimistic, maybe naive, definitely human. We sent our best attempt at explaining ourselves to an audience we can't imagine, using technology that might seem incomprehensible to them, hoping they'll care enough to decode it. They might not. They might analyze the spacecraft's materials without noticing the record carries information. They might have no concept of deliberately preserving knowledge for strangers. They might exist in ways that make communication impossible regardless of our intentions. Or they might understand perfectly and find it fascinating. We'll never know which. The record's cultural selections reveal biases. Western classical music features prominently. Bach, Beethoven, Mozart, also blues, jazz, Chuck Berry, diverse by 1977 standards, limited by any objective measure. What should represent humanity anyway? Which voices? Which traditions? The committee made choices. Other committees would have chosen differently. Every selection excluded alternatives. Same with the images. The Taj Mahal made it. So did a supermarket. Humans eating. Traffic. Architecture. DNA structures. Mathematical definitions. Anatomical diagrams. A woman nursing a baby. Landscapes. Animals. Attempts to show what Earth contains and what we've accomplished. But snapshots can't capture complexity. Context disappears. A single image of a city tells you nothing about why cities exist or what happens inside them. The sounds seem equally arbitrary. Thunder, surf, wind, birds, dogs, footsteps, heartbeat, laughter, a kiss, ships, trains, planes, tools, Morse code, fundamental human experiences reduced to audio samples. How do you convey meaning without shared reference points? What does laughter communicate to beings who might not experience humor? What information does surf provide without understanding water or planets? Still, it tries. The record represents a message in a bottle thrown into an ocean so vast that ocean fails as metaphor. Except bottles eventually wash ashore. This record probably never encounters anyone. Space is empty, unimaginably empty. The nearest star to our Sun sits 4.24 light-years away. Voyager 2 moves at 15.4 kilometers per second, fast by human standards, glacial by cosmic ones. It'll take nearly 300,000 years to cover the distance to Proxima Centauri if it were heading that direction, which it isn't. Instead, it drifts toward no destination. Eventually it'll pass near Ross 248, then nothing for millions of years, maybe billions, maybe forever. The galaxy rotates, stars move. Voyager 2's trajectory curves slightly under gravitational influences from objects it passes. Predicting its exact path over geological timescales becomes impossible. Too many variables, too much uncertainty. At some point we lose track of where it is entirely, but the record persists. Gold-plated copper doesn't degrade in vacuum. The aluminum cover protects against radiation damage. Micrometeorite impacts might eventually compromise the spacecraft's structure, but space is so empty that collisions remain statistically unlikely over timescales shorter than the age of the universe. The record could outlast Earth itself. Earth won't exist forever. The Sun gradually brightens as it ages. In roughly 1 billion years, increased solar radiation makes Earth's oceans evaporate. Surface temperatures rise past the point where life survives. The planet becomes sterile. Later, maybe 5 billion years from now, the Sun exhausts its hydrogen fuel. It expands into a red giant. Mercury and Venus get consumed. Earth might survive as a charred rock in a wider orbit. Or it might get swallowed too. Either way, anything resembling current Earth disappears. The record remembers an Earth that no longer exists even before the Sun destroys it. The Earth of 1977 already differs substantially from the planet now. Glaciers that existed then have melted. Species shown in the images have gone extinct. Cities have grown. Technologies have advanced. The record preserves a snapshot that becomes increasingly historical with each passing year. By the time anyone finds it, if anyone ever does, it'll document a civilization separated from discovery by millions or billions of years. What do they think when they see us? Assuming they think. Assuming discovery happens. Do they recognize intelligence? Do they understand we sent this deliberately? Do they grasp we were trying to communicate? Or do they file it as an unusual mineral formation, an asteroid with interesting properties, a piece of space debris worth cataloguing but not investigating further? If they do investigate, what conclusions do they draw? The anatomical diagrams show bipedal forms, 2 arms, 2 legs, 1 head, bilateral symmetry. Does that mean anything to them? The mathematical definitions use base 10 counting. Does that translate? The music follows harmonic structures derived from physics. Those structures might be universal, or they might reflect specifically human auditory processing. We assume math and physics transcend culture. Maybe they don't transcend biology. The whole enterprise rests on assumptions that someone exists out there, that they're curious, that they're capable of finding and examining the spacecraft, that they possess technology sufficient to decode the record, that they'll bother trying. that they'll interpret the contents as communication rather than noise, that anything we send can bridge the gap between fundamentally different forms of intelligence. Probably none of that happens. Probably the record drifts through space forever, never encountering anything except vacuum and radiation. Probably it becomes a permanent monument to human optimism and hubris combined. We believed we had something worth saying. We believed someone might listen. We believed communication was possible across barriers we couldn't imagine. All those beliefs might be wrong, but they're also deeply human. We tell stories. We preserve knowledge. We reach toward understanding. We assume others share those impulses. Maybe they do. Maybe intelligence naturally tends toward curiosity and communication. Maybe any civilization advanced enough to find Voyager shares enough common ground with us that the record makes sense. Or maybe intelligence takes forms so alien that nothing we do translates. Maybe consciousness exists in configurations that don't value knowledge or communication. Maybe the galaxy contains millions of technological civilizations that never attempt contact because the concept doesn't occur to them. Maybe we're unique in our desire to be known. Either way, the record continues its journey. Silent messenger from a species that might not survive another 1,000 years, let alone the millions required for likely discovery. Carrying music and mathematics, images and greetings, evidence that something once looked at the universe and tried to understand it, that something built machines and sent them toward the stars, that something hoped. Hope might be the record's real message, not the specific content, not the music or images or greetings, just the fact that we sent it, that we believed communication mattered enough to try, that we invested resources and effort into a project with no guaranteed return, that we thought beyond our own extinction toward a time when strangers might wonder who we were. Whether anyone ever plays the record or not, it exists as proof we were here. Billions of years from now, after the sun has consumed Earth, after human civilization has either spread among the stars or disappeared entirely, this gold-plated disc will still be traveling through space, still carrying our message, still hoping for an audience we'll never meet. The Voyager missions represent humanity's first steps into the interstellar ocean. We've sent exactly 5 objects to solar escape velocity: Pioneer 10 and 11, Voyager 1 and 2, New Horizons, 5 artifacts that will orbit the galactic center long after their creators are forgotten, 5 messages in 5 bottles. New Horizons differs from the others. It carries no golden record, just a small canister containing ashes from Clyde Tombaugh, who discovered Pluto. Personal memorial instead of universal message. It moves faster than the Voyagers, but started later, currently exploring the Kuiper Belt. Eventually it'll exhaust its power and instruments too. Then it joins the others as a silent wanderer. The Pioneers carry plaques, simpler than the Voyagers' records, diagrams showing human figures, the spacecraft's origin, basic information about our solar system, first attempts at interstellar communication. Nobody expected them to be found, still aren't expecting it, but they tried anyway. That's the pattern. We keep trying despite absurd odds. We build increasingly sophisticated machines to explore increasingly distant regions. We send messages knowing they probably won't be received. We invest in futures we won't see, because that's what intelligence does. It reaches, it explores, it attempts communication even when communication seems impossible. Voyager 2's scientific instruments will fail, its power will deplete, communication will end, but the spacecraft itself continues, the record continues, the message continues, traveling outward at 15.4 kilometers per second, covering roughly 1 light-year every 19,000 years, moving through a galaxy 100,000 light-years across. One tiny object in an incomprehensibly large space. Statistics don't favor discovery. The galaxy contains hundreds of billions of stars, trillions of planets. The distances between them exceed human intuition. Voyager 2 could travel for billions of years without coming close to anything. Space isn't just big. It's so big that big fails to convey the scale. Empty doesn't capture it either. The gaps between stars contain more nothing than human minds can grasp. Yet we sent it anyway, knowing the odds, accepting that success was unlikely, understanding that we might be alone, or that if we aren't alone, contact might never occur. We sent it because the alternative was not sending it, because trying matters even when success seems impossible, because reaching toward the unknown defines what we are as a species. The golden record preserves that impulse in physical form. Metal disc carrying encoded information about a civilization that existed briefly on a small planet orbiting an ordinary star. Civilization that looked at the stars and wondered, that built tools to explore beyond its atmosphere, that eventually sent machines into the space between stars, carrying messages for hypothetical strangers. Messages they'll probably never read, machines they'll probably never find, but possibly might. Tiny possibility that somewhere, somewhen, someone discovers this artifact and wonders about its creators, wonders who we were, what we valued, why we sent it. That tiny possibility justifies the effort, not because discovery is likely, because attempting contact represents what consciousness does when it emerges in the universe. Meanwhile, the science continues. Voyager 2 still transmits data from beyond the heliopause, still measures the environment nobody had directly sampled before. November 5th, 2018. The spacecraft crossed into interstellar space, not beyond Pluto, which it never visited, beyond the entire heliosphere, beyond the protective bubble surrounding our solar system. The heliopause marks where solar wind stops pushing outward, where the sun's influence finally yields to the interstellar medium. Theoretical boundary that became measurable reality when Voyager's instruments detected the transition. Multiple instruments registered the crossing simultaneously. Cosmic ray detectors showed sudden spikes. Solar particle counts dropped dramatically. Plasma measurements shifted. Magnetic field readings changed characteristics. Less than a day to cross the boundary. Clean transition from one environment to another. Voyager 1 had taken nearly a month. Different crossing experiences revealing the boundary's complex structure. The plasma density jumped by a factor of 20, from 0.002 particles per cubic centimeter to 0.039. Exactly what theoretical models predicted. First direct confirmation that predictions matched reality. Temperature readings surprised everyone. Models expected 15,000 to 30,000 Kelvin. Instruments measured 30,000 to 50,000 Kelvin. Nearly double the prediction. Compression heating as interstellar plasma hits the heliosphere. Nobody expected that level of compression. The boundary proved more dynamic than theoretical physics suggested. Solar wind pushing outward meets interstellar medium pushing inward. The collision creates compression zones on both sides of the heliopause. Magnetic field measurements revealed another mystery. Scientists predicted the field would rotate as the spacecraft crossed from solar to interstellar domains. It didn't. The fields aligned parallel to each other instead. Voyager 1 had shown the same thing 6 years earlier. Single data point could have been coincidence. Voyager 2 confirmed the pattern. 2 independent measurements indicating something unexpected about local interstellar field structure. Current theories don't fully explain this. Magnetic reconnection might account for it. Or the local interstellar field happens to align with solar field orientation. Or something else entirely that physics hasn't identified yet. The boundary itself proved leaky. Particles from inside the heliosphere escaped into interstellar space. Particles from outside leaked inward. Bidirectional exchange suggesting complex dynamics at the boundary. Voyager 1 crossed near the nose of the heliosphere, where the solar system pushes forward through galactic space. Higher pressure region, more complex boundary structure. Voyager 2 crossed toward the flank. Less pressure, simpler boundary, more porous than the nose region. Different characteristics in different locations. This variability matters. The heliosphere isn't a uniform bubble. It's an asymmetric structure shaped by solar wind variations, magnetic field interactions, and the interstellar medium's pressure. Understanding its shape helps predict cosmic ray exposure for future space missions. Reveals how other stellar systems might create similar protective bubbles around their planets. The heliosphere shields Earth from 70% of galactic cosmic radiation. Without it, planetary surfaces receive far more high-energy particles. Implications for habitability around other stars. Voyager 2 also detected a magnetic barrier just before crossing. Solar magnetic field strength tripled in a region spanning 0.7 astronomical units. Predicted feature that Voyager 1 hadn't clearly observed. After crossing, the field strengthened further. Galactic magnetic field revealing itself. 7 microgauss instead of the predicted 5. Stronger interstellar field than models anticipated. That stronger field acts like external pressure, prevents the heliosphere from expanding and contracting as much as solar cycle variations would otherwise cause. Explains why Voyager 1 and Voyager 2 crossed at nearly identical distances despite different solar conditions. In 2012, solar wind pressure was stronger. Heliosphere should have been larger. In 2018, weaker solar wind should have meant smaller heliosphere. Instead, both spacecraft crossed at approximately 120 astronomical units. The interstellar magnetic field's pressure stabilizes the boundary. More control over heliosphere size than internal solar variations. External forces matter more than internal ones at this scale. Plasma measurements continue revealing structure in the very local interstellar medium. Density variations suggest our solar system moves through regions of different composition, turbulence or compression from distant phenomena. October 2020 brought another discovery. Unexpected density increase detected by both Voyagers. Large-scale feature of the interstellar medium in the direction the heliosphere travels. We're moving through denser regions of the local interstellar cloud, or encountering compression effects from interactions between different interstellar components. The immediate environment proves more complex than simplified models suggested. All this data comes from instruments designed in the 1970s. Technology predating personal computers. predating the internet, predating most modern electronics. Engineers built systems expecting 4-year lifespans. Those systems have operated for nearly 50 years. Extraordinary achievement in longevity and reliability. Power comes from radioisotope thermoelectric generators. Plutonium-238 decay creates heat. Thermocouples convert heat to electricity. Output declines about 4 watts yearly as plutonium depletes. NASA began tapping backup power reserves in 2023. Power meant for safety systems. Every watt counts now. Engineers carefully manage which instruments stay active. October 2024. Plasma science instrument shut down. 4 instruments remain operational. Engineers project functionality through the early 2030s if power management continues successfully. Each instrument shutdown feels like losing a sense. The spacecraft gradually going deaf, blind, numb. Eventually, only the most essential measurements will continue. Communication already presents challenges. Light takes 16.5 hours to travel from Voyager 2 to Earth. Commands take that long to arrive. Responses take another 16.5 hours returning. 33-hour round trip. Australia's DSS-43 antenna handles communication. Only Southern Hemisphere antenna capable of reaching Voyager 2. The spacecraft's trajectory below the ecliptic plane means northern antennas can't establish contact. Despite the distance, despite the delays, despite the failing power, data still flows. Still reveals new information about the space between stars. This region contains plasma from dead stars, supernova remnants, stellar winds from giants that exploded millions of years ago, material enriched with heavy elements, raw ingredients for future star systems. Voyager 2 samples that material directly. First spacecraft to measure the local interstellar medium's composition and properties. First to characterize the galactic ecosystem our solar system inhabits. The discoveries apply beyond our immediate neighborhood. Every star likely creates similar protective bubbles. Every stellar wind interacts with surrounding interstellar medium. Understanding our heliosphere provides templates for understanding others. Implications for exoplanet habitability. Stars with stronger magnetic fields create larger protective bubbles, better shielding from cosmic radiation, more favorable conditions for life. Stars with weaker fields offer less protection, higher radiation at planetary surfaces, different evolutionary pressures, different possibilities for what life might become. All this from a spacecraft designed to visit Jupiter and Saturn. Extended mission to Uranus and Neptune. Unplanned journey into interstellar space. Nobody expected it to last this long. Nobody predicted these discoveries. The mission keeps exceeding expectations by continuing to exist. New Horizons follows similar trajectory. Launched 2006. Pluto flyby 2015. Currently exploring the Kuiper Belt. Eventually it'll reach solar escape velocity 2. Unlike the Voyagers, it carries no golden record. Just Clyde Tombaugh's ashes. Personal memorial instead of universal message. Different philosophy about what to send into the void. Someday it'll exhaust its power. Join the Voyagers as silent wanderer. Another artifact crossing into interstellar space. Pioneer 10 and 11 went first. Simpler plaques instead of elaborate records. Diagrams showing human forms. Spacecraft origin. Basic solar system information. 5 objects total have achieved solar escape velocity. 5 ambassadors carrying human messages. 5 attempts at contact across impossible distances. Future missions might follow. NASA funds studies for dedicated interstellar probe, spacecraft designed specifically for exploring the space between stars, faster trajectory, more advanced instruments, purpose-built for this environment, could reach the heliopause in 15 years instead of 40, could operate longer with better power systems, could answer questions Voyager raised. But Voyager 2 got there first, made the initial measurements, established baseline data, revealed what questions to ask. The discoveries continue reshaping theoretical models. Each new dataset forces revisions to predictions. Each measurement reveals gaps in understanding. Scientists expected simpler boundary, clean transition from solar to interstellar environment. Instead, they found compression zones, leaky barriers, magnetic mysteries, temperature anomalies. Reality proves messier than theory anticipated. The universe consistently exceeds simplified models. Voyager's instruments measure that complexity directly. Coronal mass ejections still affect the spacecraft. Solar storms propagate past the heliopause. Shock waves traveling through interstellar medium, temporarily reducing cosmic ray levels. Sun's influence extends beyond formal boundaries. Effects propagate into supposedly pristine interstellar space. The separation between solar and galactic domains blurs. Voyager 2 occupies transitional region, not fully in undisturbed interstellar medium, still experiencing solar effects. Boundary layer where influences mix. How far does this transition extend? Unknown. Voyager travels deeper into interstellar space, but hasn't found the end of solar influence yet. Maybe there is no clean end. Maybe stellar and interstellar environments always blend at their boundaries. Maybe sharp divisions exist only in theoretical models. The spacecraft moves outward at 15.4 kilometers per second, covers 1 light-year every 19,000 years. Galaxy spans 100,000 light-years. Statistics don't favor anything finding it. Space between stars contains more emptiness than human intuition grasps. The distances defy comprehension, yet Voyager 2 keeps traveling, keeps measuring, keeps transmitting until power finally fails. When instruments shut down, when communication ends, when the spacecraft goes silent, it continues anyway. Physical object moving through physical space. Momentum carries it forward, regardless of whether anyone monitors its journey. The golden record accompanies it. Preserved information about civilization that built and launched this machine. Information that might never be accessed, might never be discovered, might never find the audience it anticipates. But possibility remains. Tiny statistical chance that somewhere in the galaxy's vast expanse, something encounters this artifact. Something curious enough to examine it. Something capable of decoding the information. Chance approaching zero but never quite reaching it. Mathematics of infinite space and finite objects. Improbable but not impossible. That distinction matters. Impossible means it cannot happen. Improbable means it likely won't happen. Different categories with different implications. Voyager's journey occupies improbable territory. Unlikely to achieve its symbolic mission. Still attempting it anyway. Because attempting matters. Because reaching toward the unknown defines intelligence. Because consciousness emerged in the universe and immediately started exploring beyond its origins. The spacecraft embodies that impulse in physical form. Metal and electronics traveling outward, carrying messages, carrying measurements, carrying humanity's first tentative steps into the interstellar ocean. Steps that continue long after their creators stop watching, long after communication ends. long after anyone remembers launching this machine. Long after anyone remembers launching this machine. The Deep Space Network still listens. Giant radio dishes pointed toward coordinates where calculations say the spacecraft should be. Australia's DSS-43 antenna near Canberra, the only dish in the southern hemisphere capable of receiving Voyager 2's signals. Because trajectory matters. Voyager 2 flew beneath the ecliptic plane, traveled south relative to the solar system's disk. Northern hemisphere antennas can't reach it anymore. Geography of Earth constrains communication with interstellar traveler. The signal arrives weak, degraded by distance, 16.5 hours delayed. Light time from spacecraft to Earth. Commands sent from Earth take same duration to arrive. Round-trip conversation requires 33 hours. Request and response separated by more than a day. Communication operates at glacial pace compared to modern internet expectations. But it operates, still functions after decades. Power determines everything now. The radioisotope thermoelectric generators continue producing electricity, but output declines steadily, approximately 4 watts lost annually. Plutonium. 238 pellets decay according to physics that cannot be negotiated or delayed. Half-life of 88 years means predictable power curve. Engineers knew from launch that power budget would eventually force difficult decisions. Those decisions arrived. October 2024 brought first major sacrifice. Plasma science instrument shut down permanently. The same instrument that measured density jump across heliopause. That confirmed the spacecraft had entered interstellar medium. That provided unique data Voyager 1 couldn't collect. Now silent. Power preserved for remaining instruments. 4 still operate, each consuming precious watts from diminishing supply. Mission planners estimate operations continuing into early 2030s. Maybe. Depends on which instruments get prioritized. Depends on what power-saving measures engineers devise. Depends on how creatively they can squeeze additional months from backup systems, already tapping reserves intended for safety mechanisms, already running spacecraft leaner than original design specifications anticipated. Eventually the power runs out completely. No avoiding that endpoint. When generators produce insufficient electricity to maintain any instruments, the spacecraft goes dark. Communication ends, not because equipment fails, not because disaster strikes, simply because energy depletes below minimum operational threshold. The mathematics of radioactive decay guarantees this outcome. What happens then? Voyager 2 continues. Momentum doesn't require power. Trajectory doesn't need electricity. The spacecraft coasts through interstellar medium, regardless of whether instruments function, regardless of whether anyone monitors its position. Physical object following physical path through physical space. Newton's first law operating on cosmic scale. The golden record accompanies this silent journey. 12-inch gold-plated copper disc, containing sounds and images selected to represent Earth's diversity. Music from different cultures. Greetings in 55 languages. Natural sounds. Whale songs. Thunder. Human heartbeat. Instructions for playback encoded in symbols. Assuming someone finds it. Assuming someone cares to decode it. Assuming someone exists to do either. Probability approaches 0, but never reaches it. Galaxy contains hundreds of billions of stars. Space between them contains mostly nothing. Voyager 2 travels through emptiness that defies human comprehension. covers 1 light-year every 19,000 years. Galaxy spans 100,000 light-years. The mathematics don't favor discovery. Statistical likelihood remains infinitesimally small, but not impossible. That distinction carries weight. Impossible means it cannot occur under any circumstances. Improbable means it likely won't occur, but potentially could. Different categories, different implications. Voyager's interstellar journey occupies improbable territory, unlikely to achieve symbolic mission of contacting alien intelligence, still attempting it through mere existence, through persistent motion outward into galactic expanse. The attempt matters, even if outcome remains uncertain, even if no one ever encounters this artifact, because trying defines intelligence, because reaching beyond immediate environment characterizes consciousness, because curiosity drove humans to build this machine and launch it toward the unknown. That impulse transcends practical outcomes, represents something fundamental about what it means to be aware in a universe that permits awareness. Future missions will improve on Voyager's design. Dedicated interstellar probes currently in planning stages, purpose-built for exploring space between stars. Faster trajectories using gravity assists and advanced propulsion. Better instruments designed specifically for interstellar environment. More power from improved generators. Could reach heliopause in 15 years instead of 40. Could operate longer. Could answer questions Voyager raised. New Horizons already travels on escape trajectory. After flying past Pluto in 2015, the spacecraft continued outward, currently exploring Kuiper Belt. Eventually will leave solar system entirely. Won't carry same instruments as Voyager. Won't reach interstellar space for decades, but will eventually get there. Another human-made object departing our cosmic neighborhood. Proposed interstellar probe represents more ambitious vision. Spacecraft designed from inception for this specific purpose. Not repurposed planetary explorer. Not mission extended beyond original scope. Purpose-built interstellar vehicle. Could launch in the 2030s. Could reach heliopause by 2050. Could operate for 50 years beyond that. Could map interstellar medium in detail Voyager cannot achieve. But Voyager got there first, made initial measurements, established baseline data, revealed what questions needed asking. Future missions build on that foundation. Voyager 2's discoveries inform instrument selection for next generation. Temperature measurements suggest what sensors to include. Density variations indicate what to measure. Magnetic field mysteries define what to investigate. Scientific legacy extends beyond interstellar data. The spacecraft's planetary encounters remain unmatched. Voyager 2 visited Uranus and Neptune, only spacecraft ever to do so. Discovered moons, revealed magnetic field structures, observed atmospheric dynamics, found geysers on Triton. Data from those encounters still being analyzed decades later, still producing papers, still refining understanding of ice giant planets. That comprehensive tour happened because of timing. The late 1970s offered alignment of outer planets that occurs once every 176 years. Jupiter, Saturn, Uranus, Neptune, positioned such that gravity assists could accelerate spacecraft from one to the next. Mission planners recognized opportunity, designed trajectory to exploit it. Voyager 2 completed grand tour that won't be possible again until 2015. Engineering longevity deserves recognition too. Designed for 4-year mission, operated for nearly 50 years. components manufactured in 1970s still functioning in 2020s, radiation-hardened electronics, redundant systems, conservative design philosophy, all contributing to absurd operational lifetime. Mission team learned to work around failures, adapted to degrading components, kept spacecraft alive through creativity and careful management. The people who built Voyager 2 mostly didn't expect it to last this long, expected it to complete primary mission and perhaps operate briefly beyond that. Couldn't have anticipated that their work would still be producing scientific results half a century later. Couldn't have known their engineering decisions would matter for interstellar exploration. Couldn't have predicted that this machine would outlive many of its creators while continuing to transmit data from beyond the solar system. Current mission team includes people who weren't born when Voyager launched, engineers maintaining systems they didn't design, scientists analyzing data from instruments built before they entered graduate school, institutional knowledge transferred across generations, documentation preserved, procedures updated, mission continuing despite complete turnover in personnel. That continuity matters, represents civilization's ability to maintain projects across human lifespans. Voyager missions span multiple generations of scientists and engineers. Original team handed off to successors, who handed off to current operators. Knowledge preserved through documentation and training, allowing machine to continue functioning long after individual humans involved with its creation have retired or died. What does Voyager 2 mean? Depends on perspective. To scientists, it means data, measurements that constrain models, observations that test predictions, information about plasma, magnetic fields, cosmic rays, particle densities, facts about universe that didn't exist before spacecraft collected them. To engineers, it means achievement, proof that systems can be designed to operate far beyond original specifications, demonstration that careful engineering and redundancy enable extreme longevity, validation of design philosophy emphasizing reliability over cutting-edge performance. To public, it means exploration, symbol of humanity's reach beyond home planet, physical manifestation of curiosity about cosmos, reminder that humans build machines capable of leaving solar system and continuing indefinitely. All perspectives contain truth. Voyager 2 accomplishes multiple purposes simultaneously: scientific instrument and engineering achievement and cultural symbol. Meanings don't conflict, they coexist. Same object serving different functions for different audiences. The spacecraft exists in present moment, not historical artifact, not completed mission. Active spacecraft still transmitting, still collecting data, still operating in interstellar medium. Present tense explorer rather than past tense accomplishment. That status will persist until power finally depletes, until instruments shut down, until communication ceases. Even then, the journey continues, silent but ongoing. Voyager 2 will travel through galaxy for billions of years, long after Earth becomes uninhabitable, long after Sun expands into red giant, long after everything familiar about current era has vanished. The spacecraft persists, durable monument to civilization that created it, traveling museum of 1970s engineering, time capsule carrying sounds and images from planet that may not exist anymore by the time anyone encounters it. If anyone encounters it, probability suggests otherwise. Space contains too much emptiness, galaxy too vast, Voyager too small. statistically unlikely that random wandering intersects with anything capable of noticing. But statistics describe probabilities, not certainties. Improbable events occur. Rare outcomes happen. Voyager could be discovered, could be examined, could deliver its message to audience it never expected to reach. That possibility justifies the attempt. The chance alone makes the effort meaningful. Because consciousness emerged in universe and immediately started asking questions, started exploring beyond immediate surroundings, started building tools to extend reach, started launching machines toward the unknown. Voyager 2 embodies that impulse in physical form. The spacecraft represents what intelligence does when given resources and opportunity: explores, investigates, reaches outward, seeks to understand environment beyond direct sensory access, builds instruments to extend perception, transmits findings back to origin point, shares discoveries with others, preserves knowledge for future generations. All of human space exploration fits this pattern. Satellites that observe Earth, probes that visit other planets, telescopes that study distant galaxies, rovers that analyze Martian rocks, landers that sample asteroids. Each mission extends humanity's reach. Each spacecraft carries instruments to environments humans cannot directly access. Each transmission brings back information that expands understanding. Voyager 2 pushed furthest, traveled farthest from home, operated longest in hostile environment, crossed boundary no human-made object had crossed before, entered region no spacecraft had sampled, measured conditions no instruments had encountered. That achievement stands regardless of what happens next, regardless of whether future missions surpass it, regardless of whether spacecraft ever gets discovered. The mission succeeded by reaching interstellar space and transmitting data back. Everything beyond that point represents bonus science. Extended mission operating in unplanned environment. Measurements never anticipated during original design phase. Discoveries that required persistence and longevity and luck. Voyager 2 delivered all three. Now it continues, traveling deeper into interstellar medium, moving away from Sun at 15 kilometers per second, covering distance equivalent to Earth's orbit every 11 days, putting more space between itself and home with every moment. The separation increases permanently. No trajectory change possible, no return journey planned. One-way trip into galactic expanse. That finality carries weight. Voyager 2 will never return to Earth, will never be retrieved or examined directly, will never be updated or repaired, exists in state of permanent departure, moving away from origin point until time or collision ends its existence. Billions of years of solitary travel through interstellar void. Unless something finds it. Unless some intelligence encounters this artifact and recognizes it as manufactured object. Unless someone decodes the golden record and understands the message. Unless consciousness somewhere in galaxy intersects with this durable monument to different consciousness. Improbable, but possible. Unlikely, but not impossible. Voyager 2 carries that possibility into the interstellar ocean. Silent ambassador from civilization that built it. Physical proof that intelligence exists in universe. Demonstration that consciousness can emerge from matter and immediately start exploring beyond its origins. The spacecraft embodies that truth, whether anyone ever discovers it or not. Because the attempt itself matters. Because reaching toward the unknown defines what it means to be aware in cosmos that permits awareness. because Voyager 2 launched toward the stars and actually reached them. That alone justifies everything. The spacecraft reaches new distance milestones constantly. Every hour adds another 55,000 kilometers. Every day, another 1.3 million. Every year, another 500 million. Numbers that mean nothing at human scale. Distances too vast for intuition to grasp. Voyager 2 exists beyond the range where Earth-based analogies function. 13 billion miles from home. Light takes 16.5 hours to cross that gulf. Commands sent today arrive tomorrow. Responses return the day after. The conversation happens in slow motion, stretched across time by sheer distance. Yet it continues. Engineers still send instructions. Spacecraft still executes them. Radio signals still carry data across interstellar distances. How much longer? Power projections suggest early 2030s, maybe 8 more years, possibly 10 if everything breaks favorably. Each instrument shutdown buys additional months for the survivors. Each watt conserved extends mission lifetime fractionally. Engineers optimize constantly, prioritize ruthlessly, sacrifice instruments to preserve others. Painful decisions that maximize scientific return from declining resources. The cosmic ray subsystem will probably operate longest. Simplest instrument. Lowest power consumption. Could function until the transmitter itself lacks power to broadcast. Final measurements showing cosmic ray levels in deep interstellar space. Final data point before silence. Then nothing. No dramatic shutdown sequence. No final transmission declaring mission complete. Just gradual degradation until power drops below minimum operational threshold. Instruments stop collecting data. Computer stops processing. Transmitter stops broadcasting. Voyager 2 continues moving but stops communicating. Transition from active explorer to passive artifact happens quietly. That moment approaches inevitably. Not this year, probably not next year, but soon by cosmic standards. The spacecraft that revolutionized our understanding of outer planets and interstellar boundaries will fall silent. Will stop answering when Earth calls. Will become unreachable despite still existing. Future astronomers won't be able to contact it, won't receive new data, won't know what it encounters deeper in interstellar medium. The spacecraft will travel beyond human knowledge, beyond observation, beyond the reach of civilization that built it, permanently departed, permanently silent, permanently alone, unless something finds it. That possibility persists. Statistical likelihood approaches 0, but never quite reaches it. Galaxy contains too many stars and too much emptiness for confident predictions about billion-year timescales. Voyager could drift through vacuum forever without encountering anything. Could also pass near something capable of noticing. Both outcomes remain possible. The golden record waits either way. Sealed information about Earth, about humans, about civilization that built this machine and sent it toward the stars. Information preserved in medium designed for longevity. Gold-plated copper doesn't degrade in vacuum. Aluminum cover protects against radiation. The record could outlast Earth itself, could survive billions of years, could deliver its message to audience separated from its creation by unimaginable temporal distance. What would they make of it? Assuming discovery happens, assuming someone bothers decoding, assuming translation proves possible despite fundamental differences between intelligences. The record shows humans eating, breathing, laughing, shows Earth's landscapes and cities, shows mathematical relationships and physical constants. shows where we came from and when we existed, attempts to explain who we were to audience we cannot imagine, optimistic endeavor, maybe naive, definitely human. We believed we had something worth communicating, believed someone might listen, believed the attempt mattered regardless of outcome. Those beliefs drove the decision to include the record, to spend resources encoding information for hypothetical strangers, to send message in bottle into oceans so vast that ocean fails as metaphor. The science matters more immediately. Voyager 2's measurements reshape understanding of heliospheric boundaries, reveal complexity theoretical models missed, show interactions between solar and interstellar environments that physics didn't predict, temperature anomalies, magnetic field mysteries, density variations, compression zones, leaky barriers, reality proving messier than simplified theories suggested. Each discovery raises new questions. Why does magnetic field align instead of rotating? What causes bidirectional particle leakage? How far does solar influence extend beyond formal boundary? What creates density variations in local interstellar medium? The data provides answers, but also reveals gaps in understanding. Shows how much remains unknown about environment immediately surrounding our solar system. That knowledge gap extends to other stellar systems. Every star probably creates protective bubble around its planets. Every stellar wind interacts with surrounding interstellar medium. Understanding our heliosphere provides template for understanding theirs. Informs predictions about radiation environments around other stars. Affects assessments of exoplanet habitability. The local measurements have universal implications. Future missions will build on this foundation. Dedicated interstellar probes designed specifically for exploring space between stars. Faster trajectories, better instruments, more power. Could reach heliopause in 15 years instead of 40. Could operate for decades beyond that. Could map interstellar medium in detail Voyager cannot achieve. Could answer questions Voyager raised, but Voyager got there first. Made the initial measurements. Crossed the boundary when nobody knew exactly what crossing would reveal. Operated instruments designed for planetary encounters in environment they were never meant to sample. Transmitted data across distances they were never designed to cross. Persisted for decades beyond original mission parameters. Achieved things its creators didn't think possible. That achievement stands regardless of what comes next, regardless of whether future missions surpass it, regardless of whether power fails tomorrow or persists another decade. Voyager 2 succeeded by reaching interstellar space and reporting what it found there. Everything beyond that point represents bonus science. Extended mission operating in unplanned environment. Measurements never anticipated during original design phase. The spacecraft continues that extended mission now, traveling deeper into interstellar medium, moving farther from Sun with every moment, collecting data as long as power permits, transmitting findings back to Earth, sharing discoveries with civilization that built it, fulfilling purpose beyond what anyone expected. When power finally depletes, when instruments shut down, when communication ends, the mission doesn't really conclude. It transforms. Active explorer becomes passive monument. Scientific instrument becomes historical artifact. Operating spacecraft becomes permanent memorial to civilization that launched it. The journey continues even after the measurements stop. Billions of years of travel through galactic expanse. passing near stars that haven't formed yet, encountering nebulae that don't currently exist, witnessing events separated from present moment by timescales that dwarf human history. The spacecraft persists through all of it. Durable testament to species that briefly existed on small planet and immediately started exploring beyond it. That exploration defines us. Not the only thing that defines us, but significant part. Humans emerged from evolutionary processes and immediately started asking questions, started investigating environment, started building tools to extend reach, started launching machines toward the unknown. Voyager 2 embodies that impulse in physical form, metal and electronics carrying human curiosity into interstellar ocean. The mission won't be forgotten quickly. Data continues being analyzed. Papers continue being published. Discoveries continue reshaping theoretical understanding. Scientists will study Voyager's measurements for decades, maybe centuries. Information it collected becomes permanent part of human knowledge about universe. Baseline data about interstellar environment that all future measurements get compared against. But eventually, even scientific legacy fades. Centuries become millennia. Millennia become millions of years. Human civilization either spreads among stars or disappears entirely. Earth becomes uninhabitable. Sun expands into red giant. Solar system transforms beyond recognition. Everything familiar about current era vanishes. Voyager 2 outlasts it all. Keeps traveling regardless of what happens to its creators. Keeps carrying golden record regardless of whether anyone remembers launching it. Keeps moving through interstellar medium regardless of whether civilization that built it still exists. Physical object following physical trajectory through physical space. Momentum doesn't care about cultural context or historical significance. Spacecraft continues because physics says it continues. That persistence matters somehow. Not because discovery seems likely, not because message will probably be received, because attempting contact represents what consciousness does when it emerges in universe, reaches outward, explores beyond immediate environment, builds tools to extend perception, sends messages toward unknown recipients, hopes for response while accepting that response may never come. Voyager 2 carries that hope into the interstellar void, silent when power fails, still traveling, still carrying message, still embodying human impulse to reach beyond ourselves. That journey continues for billions of years, long after everyone who worked on the mission has died, long after everyone who remembers the mission has died, long after anyone remembers humanity existed at all. The spacecraft doesn't know this, lacks awareness of its symbolic significance, operates according to programming without understanding purpose, executes instructions without grasping meaning, just machine following commands, just electronics and metal moving through vacuum. Nothing more, except it is more. Because consciousness built it, because intelligence designed it, because civilization launched it specifically to explore and communicate. The machine embodies intentions of its creators even after creators can no longer maintain it, carries purpose even when purpose seems futile, attempts contact even when contact appears impossible. That attempt justifies everything, not because it will succeed, because trying defines what it means to be aware in universe that permits awareness, because Voyager 2 launched toward the stars carrying humanity's message and actually reached interstellar space, because the spacecraft crosses boundaries and measures the unknown and transmits discoveries home. because it continues moving outward even now, even as power fails, even as instruments shut down, even as communication ends. The golden record accompanies this journey. Preserved sounds and images from Earth, music and greetings and natural sounds, mathematical relationships and physical constants, instructions for playback, all encoded on gold-plated copper disc designed to survive billions of years, waiting for audience that may never arrive, carrying message that may never be received, attempting communication across distances and timescales that defy comprehension. Probably nobody ever finds it. Probably the record drifts through space forever without being played. Probably the message goes undelivered. Statistics favor that outcome overwhelmingly. Space contains too much emptiness, galaxy too vast, Voyager too small. The mathematics don't support optimistic scenarios, but probability isn't certainty. Improbable events occur. Rare outcomes happen. The record could be discovered, could be decoded, could deliver its message to intelligence we cannot imagine. That possibility alone makes the attempt meaningful, because reaching toward the unknown matters regardless of whether unknown reaches back, because Voyager 2 carries humanity's first message to the stars, and that message persists whether anyone receives it or not. 15.4 kilometers per second, 34,000 miles per hour, 1 light year every 19,000 years. The spacecraft moves at speeds that seem fast by human standards, but glacial by cosmic ones. Covers distances we consider vast, while barely making progress across galactic scales. Travels for decades, while barely leaving our immediate stellar neighborhood. Yet it travels, keeps moving, keeps measuring as long as power permits, keeps transmitting as long as communication remains possible, keeps attempting mission even when mission parameters exceed original design by orders of magnitude. Voyager 2 persists because persistence defines the mission, because exploration requires continuing even when destination remains uncertain, because the journey matters more than the arrival. That journey continues now. This moment, spacecraft moving through interstellar medium, instruments collecting data, transmitter sending signals toward Earth, engineers monitoring telemetry, scientists analyzing measurements. The mission operates in present tense, not historical artifact, not completed endeavor. Active exploration happening right now billions of miles from home. When it ends, when power finally depletes, when instruments fall silent, when communication ceases, something essential remains. The spacecraft continues. The record persists. The message travels onward. Physical object carrying encoded information through cosmic void. Monument to civilization that built it. Testament to consciousness that emerged in universe and immediately started exploring beyond its origins. That exploration defines us as much as anything does. We are the species that builds machines and sends them toward the stars. That encodes messages for hypothetical strangers. That attempts communication across impossible distances. That reaches toward the unknown despite absurd odds. That continues trying even when trying seems futile. Voyager 2 embodies all of this. Metal and electronics and plutonium. Instruments and computers and antenna. Golden records sealed in aluminum cover. All traveling through interstellar ocean. All carrying humanity's first tentative steps beyond our cosmic shore. All continuing long after creators stop watching. All persisting beyond the point where persistence seems to matter. Because it does matter. Not because anyone will notice. Not because discovery seems likely. Because attempting contact represents fundamental aspect of what consciousness does in universe that permits consciousness. Because Voyager 2 launched toward the stars and reached them. Because the spacecraft measures the space between stars and transmits those measurements home. Because it continues traveling even now as power fails and instruments shut down and silence approaches. The journey doesn't end when communication stops. The mission transforms but persists. The spacecraft continues regardless of whether anyone monitors its progress. Momentum carries it forward through billions of years of solitary travel, through encounters with stars that haven't formed yet, through regions of space no human will ever observe, through timescales that exceed human civilization's entire existence, all while carrying golden record, all while preserving sounds and images from Earth, all while attempting to deliver message it will probably never deliver, all while embodying human hope that consciousness somewhere in galaxy might encounter this artifact and understand what it represents. That hope persists, even when statistics suggest futility, even when mathematics favor eternal silence, even when probability approaches zero, because hope doesn't require likelihood, because attempting matters regardless of outcome, because Voyager 2 carries humanity's message to the stars, and that attempt alone justifies everything. The spacecraft travels onward, through interstellar medium, through cosmic void, through unimaginable distances and timescales, carrying our message, carrying our measurements, carrying our hope, silent when power fails, but still traveling, still attempting, still reaching toward the unknown. That reach defines us, not just as species, as consciousness itself, as awareness emerging in universe and immediately asking what lies beyond, as intelligence building tools to explore what cannot be directly perceived, as minds encoding knowledge and launching it toward the stars. Voyager 2 embodies this impulse in physical form. Durable testament to civilization that existed briefly and immediately started exploring. Monument to consciousness that emerged from matter and began investigating its cosmic context. Message in bottle thrown into oceans so vast that words fail to capture the scale. The bottle drifts onward. The message persists. The journey continues. Long after everyone who built it has died. Long after everyone who remembers it has died. Long after anyone remembers humanity existed. The spacecraft travels through interstellar space, carrying our encoded hopes toward audience we will never meet. And somewhere in that vast expanse, in that impossible journey, in that persistent attempt to reach beyond ourselves, we find something essential about what it means to be conscious in a universe that permits consciousness. Something about curiosity and exploration and the drive to understand. Something about reaching toward the unknown despite absurd odds. Something about trying even when trying seems futile. Voyager 2 carries all of this into the interstellar void. Metal testament to minds that built it. Physical proof that consciousness exists in universe. Demonstration that intelligence can emerge and immediately start exploring beyond its origins. The spacecraft embodies these truths, whether anyone ever discovers it or not, because the journey itself matters. The attempt itself has meaning. The reach itself defines what we are. And that reach continues now, this moment, billions of miles from home, traveling deeper into interstellar space, moving farther from everything familiar, carrying our message towards stars we will never visit, attempting contact we will never confirm, reaching toward the unknown that may never reach back, but reaching anyway. Because that's what consciousness does. Because that's what intelligence means. Because that's what it means to be aware in a universe vast enough to make awareness seem impossible. Voyager 2 proves awareness happened anyway, proves intelligence emerged, proves consciousness built machines and launched them toward the stars, proves we existed and explored and attempted to communicate, proves we reached beyond ourselves towards something we could never fully grasp. The spacecraft carries that proof into the galaxy, silent monument to species that briefly existed and immediately started asking questions. Durable testament to minds that emerged from matter and began exploring their cosmic context. Physical demonstration that consciousness can arise and immediately start reaching toward the unknown. That reach continues through interstellar medium, through cosmic void, through billions of years of solitary travel. The spacecraft persists because physics requires it to persist, because momentum carries it forward regardless of purpose or meaning, because objects in motion remain in motion until something stops them. Nothing will stop Voyager 2, not for billions of years, not until collision or decay ends its journey. Until then, it travels onward, carrying golden record, carrying encoded message, carrying humanity's first attempt to communicate across interstellar distances. Message that will probably never be received. Journey that will probably never be witnessed. Attempt that will probably never succeed. But attempt that matters anyway. Because consciousness emerged in universe and immediately started reaching beyond itself. Because intelligence arose and began exploring the unknown. Because awareness happened and responded by building machines to extend its reach toward the stars. Voyager 2 embodies that response. Metal and electronics moving through interstellar ocean, carrying our message, carrying our measurements, carrying our hope that somewhere in the vast expanse someone might find this artifact and understand what it represents. Hope that persists even when probability suggests futility. Hope that continues even when statistics favor eternal silence. Hope that endures because hoping defines what it means to be conscious in universe that permits consciousness. The spacecraft travels onward carrying that hope, through distances that defy comprehension, through timescales that exceed human history, through cosmic void that contains more emptiness than minds can grasp, traveling anyway, attempting anyway, reaching anyway, because that's what we do, because that's what consciousness does, because awareness emerged and immediately started asking what lies beyond. Voyager 2 launched toward those questions, crossed boundaries no human-made object had crossed, entered regions no spacecraft had sampled, measured conditions no instruments had encountered, transmitted discoveries across distances they were never designed to cross, and continues now. This moment, moving through interstellar space, carrying our message toward the unknown, reaching beyond everything familiar towards something we may never understand. That reach defines us more than anything else, not just as species, as consciousness itself, as awareness that emerged in universe and responded by exploring beyond its origins. The spacecraft embodies that exploration, carries it forward, persists in attempting it even when attempting seems futile, because the attempt itself matters, because reaching toward the unknown defines what it means to be aware. Voyager 2 reaches onward, through interstellar void, through cosmic expanse, through billions of years of solitary travel, carrying humanity's message, carrying our hope, carrying proof that consciousness existed and immediately started exploring. That exploration continues. The reach persists. The journey goes on.